The last topic that we are going to cover in this chapter is on resonance. We have actually dealt with resonance many times in our lives, though we may not have known it. Here are some classic examples of where you might see resonance. You've probably heard that when you play a loud sound, especially at a particular pitch, it causes glass to shatter. We often think of this as an opera female singer sings very high notes, very powerfully, all the glass shatters. Well, it is possible to make glass shatter with your voice, but it doesn't have to be a high female opera singer's voice. What has to happen is the pitch of the trumpet has to match the frequency of the glass, and I'll explain that in a second. Here in the figure on the bottom is a bridge that was completely destroyed during an earthquake. So you have an earthquake, induces waves, causes the bridge to shake, causes resonance, breaks the bridge apart. Let me explain what resonance is. First of all, we need to talk about the natural frequency. Every object naturally oscillates at a particular frequency. That frequency is called the natural frequency. And it follows the same frequency equation we saw for simple harmonic motion. So every object has one particular natural frequency. Why this is important is as follows. You have forced vibrations. Forced vibrations occur when there is some periodic driving force. So in the first example, a picture on the previous slide, we have a glass that has a bunch of sound waves from the trumpet blasted at the glass. So the sound waves from the trumpet are your periodic driving force. In the second figure, the bridge of the earthquake was the periodic driving force. Now, that force may or may not have the same period as the natural frequency of the system. The trumpet might be playing at one note, but that note may not match the natural frequency of the glass. The earthquake may have a certain frequency, but that may not match the frequency of the bridge. But if it does, if the frequency of the periodic driving force is the same as the natural frequency, then the amplitudes become quite large. And that's what's called resonance. I'll have a couple of videos of examples of resonance. One of a rock singer who does break a wine goblet with his glass, and also another of the Tacoma Narrows Bridge. I'll have that on Falcon Online for you. So the sharpness, so let's take a look at this picture here at the bottom. You have your driving force down here and the frequency that it oscillates at. So if you have a driving force that oscillates, say, at this frequency, then the oscillating system, whatever it is that's being affected, won't be oscillating very hard at all. So, for example, you may have a sink full of water. A sink full of water, and you just start bobbing something up and down very quickly in the water. You just create a bunch of ripples, but the amplitudes of those ripples are pretty small. This is what we're talking about here. But if I change the frequency at which I'm bobbing the object in the water, what I'll see is that the amplitude of the water can change. And then pretty soon, if you've got it just right, that the frequency that you're bobbing something into the water matches the natural frequency of the water itself, then you'll see the waves in the water just suddenly become extremely large. Now the sharpness of, or how large that amplitude can get, depends on the damping. If the damping is small, then you can get a very sharp and extreme amplitude. However, if you have a large amount of damping, then you get a very small, less sharp amplitude. Let's finish this by talking about a very simple example where you get resonance. Out in the air, well, out in the public, multiple radio stations are broadcasting music, news, talk shows, whatever. They're all broadcasting at their particular frequency at the same time. So basically, you've got all of these frequencies down here that are that have radio broadcasts. Now you sit in your car and you turn the tuner, and the tuner sets it so that its antenna will vibrate at a particular frequency. As such, it will that antenna will then vibrate at the tuned frequency, and so you only pick up the radio waves from that particular radio station that broadcasts at that frequency. So that's how the radio works in your car, is purely on resonance.